All right, recording has started, it seems.
Yeah.
So, yeah, thank you. Good evening, everyone. So I'll just do a quick recap of what we did last time, what we discussed last time. And feel free to ask any questions, interrupt me at any point. Right, so we started with the face coloring version of the four color conjecture, which says that every plane graph is four face colorable. And of course, this is not actually where we started. We looked at the raw version of it, right? And then we understood that it is basically a statement in graph theory. And then we discussed plane duality briefly, and we converted this into a problem about all planar graphs. The advantage is that now you don't need an embedding. Now you don't need a drawing. You can just talk about a planar graph, right? And it says that, I'll explain Tate edge coloring. Yeah. So we basically observe that this is equivalent to showing that every planar graph is four vertex colorable, right? And this version doesn't need an embedding, so that's nice. And we also discussed the history. So the conjecture was proposed in 1852-53 by Guthrie, and then there are multiple failed attempts. We discussed two of them briefly. And then finally, the conjecture was proved 124 years later in 1977. This was controversial. Eventually, it seems that the authors corrected all the mistakes, but it was still a computer-assisted proof with 1,800 cases. People were not happy. 1997, this was simplified, but the simplified proof still has 600 cases. So still not happy, right? So that is where we are. And 1879, there was a failed attempt by Alfred Kemp. And that mistake in Kemp's proof was found by Hewood 11 years later in 1890. And Hewood was able to use some of Kemp's ideas and, of course, their own ideas to prove the five color theorem, which we will see today. We will see five color theorem, the proof due to Hewood today, apart from other things. And then there was another failed attempt by Tate. But the good thing that Tate did was Tate gave an equivalent formulation, which actually led to whole branches of research in graph theory, including my own area of research, matchings, perfect matchings, but also another beautiful area called flows. You can read about flows in graphs. These are group flows, not other kinds of flows. So all of this basically comes from Tate's equivalent formulation, the study of matchings and the study of flows. Right. And Tate's proof was incorrect. That was discovered again 11 years later by Peterson, who also discovered the beautiful Peterson graph. This was in 1891. Right. And what we did discuss last time is we sort of saw what Tate's version is. We did not prove that it is equivalent. We sort of proved one direction without writing a rigorous proof. I kind of just gave you the main idea, and of course, it has to be completed. So I will just quickly, since there was a question on the chat, can you explain Tate edge coloring? I will quickly explain what Tate's edge coloring version is, right? So I'll do it by an example. Here is a three connected, three regular planar graph. What Tate says is that if you can color all such graphs using three colors, the edges of all such graphs. Now we are not coloring faces or vertices. Now Tate wants to color edges. So Tate says if you can color the edges of this graph using three colors, let's say red, blue, and green. So let's say I color this edge red, but now any edge adjacent with this edge, adjacent here means they share a vertex. It should not get the red color. So therefore, the second edge I'll have to give another color, let's say blue. And now the third edge incident at this vertex can't get red, can't get blue. So therefore, I must give it the third color, green. If I can color every three connected, three regular planar graph, the edges of it using three colors in such a way, then we have proved the four color conjecture. This is what Tate observed. So let's look at such a coloring of this graph. Right? If the 4-color conjecture is true, then this graph should be colorable like this. So here is basically the only way to color this graph. This graph is very small. So it is uniquely 3-edge colorable up to permutation of colors. Here is the 3-edge coloring of this graph. And Tate also explains how you can go from a 3-edge coloring to 4-vertex coloring, right? Yeah. This part we did not discuss. What we did discuss is we took a 4-face coloring, my bad. We took a 4-face coloring and we went to a 3-edge coloring. But Tate also proves that from a 3-edge coloring, you can go to a 4-face coloring. Right? Yeah. Okay. So any questions regarding Tate's edge coloring version? We did not prove it. So if you're asking about the proof, well, the answer is I did not actually show you the entire proof last time. Okay, thank you. So back to the previous page. Any questions, concerns regarding all of this? Okay. So if not, the main goal today is to prove the 5-color theorem. Okay. However, before we prove the 5-color theorem, we will prove some other things, simpler things maybe. We will actually prove the 6-color theorem first. But before we even prove the 6-color theorem, I want to go to something more basic than that. So, what do you all think? Are trees 2-colorable? I'm talking about vertex coloring. Let me pose a question. Here is my question. Are trees 2-vertex colorable?
Yes.
Yes? Okay. And how would you prove this?
You can just look at
We color like each sort of level, like alternate. We
My
color.
definition of tree is just a connected acyclic graph. I have no concept of levels and all that. I know what you mean, but I
okay, you can start with the root vertex and look at each of its neighbors. You
Yeah,
have to find
the
neighbors in a
minimum
nice way.
distance of each of the vertex from the root vertex can be used to define the level, right? So if it's odd, then we color it in like red, and if
but can we do
We
something?
can make it a bipartite graph.
Yeah, so proving that it is 2-colorable is the same as proving it is bipartite. So can we get an even simpler proof? I want as simple a proof as possible.
There are no cycles, therefore there are no odd cycles.
No, then you're using a theorem saying that every graph without odd cycles is 2-colorable. I don't know this theorem. Let's say I don't know this theorem. Right? So that is a much stronger statement, right? Proving that every graph without odd cycles is 2-colorable, 2-vertex colorable, is a much stronger statement than saying that trees are 2-colorable. So can you give me an even simpler proof for trees
induct.
2-colorable?
We can induct, right?
Induct. Yes, please induct. What will you induct on?
Probably
Number
the
of
vertex.
vertices.
Yeah.
Number of vertices.
Yeah.
Okay.
Yes.
Okay. And what is your, so you have a big tree and you want to get a smaller tree. So what will you do to get a smaller tree?
We'll
Yes.
remove sort of the leaf.
Leaf.
I think it was
Let's
called.
remove a leaf. Okay, so we have to prove existence of a leaf in any tree on 2 or more vertices. If we prove that, this is a simple exercise, I will not prove it. If we prove that there is a leaf and we observe that deleting a leaf from a tree gives a smaller tree, then by induction hypothesis, the smaller tree is 2-vertex colorable. But we deleted a leaf. So this vertex we deleted, V, it was adjacent to only one vertex in the smaller tree.
So we color it with the opposite color.
Opposite color. We are done. Right? Okay, excellent. So let's prove this. The answer is yes. And the main points are: 1, show existence of a leaf in every tree of order. By order, I mean number of vertices. Order at least 2. Right? And then use deletion of leaf to finish the proof by induction. Right? Just to give us pictorial representation, if this is my tree, I don't know, well, this is not a cycle, this is an abstract drawing. There is a leaf, vertex of degree 1. I will look at this T minus V. T minus V is this, whatever you see here. I will take a 2 vertex coloring of this graph. Now, because this fellow is a leaf, it is only one neighbor, U. Let's say you got a color, my colors are red and blue. Let's say you got the color blue without loss of generality. Then I will take the color red and give it to this fellow. And now I have 2 vertex coloring of the original tree. Yeah. And of course, every inductive proof is a base case. What is the base case?
Just a single like proof.
Single vertex tree. K1, complete graph on one vertex. Why not? That's a tree. That is 2 vertex colorable. In fact, there's 1 vertex colorable. We are done. Okay, great. So, this is nice. Now, can somebody generalize this? So, we use the fact that there exists a vertex of degree 1 and we somehow use this to finish off our proof. Can we generalize this observation?
If we can
Degree of k minus 1 for all number of colors you're using. So like you need a vertex whose degree is 1 less than the number of colors you are allowed to
Sure.
use.
Supposing the number of colors is k, you want a vertex of degree at most k minus 1.
yes.
Yes.
Yeah?
Yeah.
Okay. So, does that mean that if I have a graph that has a vertex of degree at most k minus 1, then does it mean that that graph is k vertex colorable?
Yes.
Yes.
No,
Yes.
like it can have a K cycle in it.
Good. Think
Why
about it.
would that make a difference?
Yeah, so that's a good question. So let's look at the subtlety here. So my question is, G is a graph that has a vertex of degree at most k minus 1. Okay, we use the fact that there is a leaf that is degree at most 2 minus 1, 1. Okay, then G is k vertex colorable. Is that a true statement? Or can you find a counter example?
I think it should be true because you can do the same argument over here with V as your vertex. Pick out a vertex by the same induction, whatever vertices are adjacent to it, which are connected
Oh,
by
but
the edge.
that's the thing, right? So you deleted this vertex.
But
Now
there's
you
a
have to apply
problem.
the induction hypothesis.
But
No, you
like
don't.
it has to be like all vertices must have less than K, less than equals K.
Okay, so if all vertices of degree at most k minus 1, then I'm willing to believe
Yeah.
this statement.
Yeah.
But what if there is only one vertex of degree at most k minus 1?
Then it can be deleted and like it can happen all vertices have more than K.
Exactly. Exactly. Right? So just the existence of a vertex is not what we are using. We are using a stronger statement, which is that in every tree, there is a vertex of degree 1. Not just in this tree, but in every tree.
All right.
In particular, when you delete a vertex, you again have a tree. Therefore, you can apply the induction hypothesis. You agree? Okay. So, the property we are using here, when you delete a vertex from a tree, again you have a tree. Right? That is when you can apply the induction hypothesis. So that means when I delete this vertex of degree at most k minus 1, if I want to apply induction, I again need in the smaller graph a vertex of degree at most k minus 1. Then I can apply the induction hypothesis.
And that may not exist.
Right, exactly. So we need to make a stronger. So my question here, the answer is no. You can easily consider counterexamples, concrete counterexamples, not just abstract, right? But now can we make a correct statement out of this? Can someone try and make a correct statement out of this? So my current statement is, I have a graph that has a vertex of degree at most k minus 1. This is not enough. Can you make it stronger? Then the conclusion should become true.
If every vertex had degree k less than k minus 1, it's too strong. But
It is too strong. Yeah. Can you find an intermediate point?
yeah.
Yeah, because for example, in a tree, if I say every vertex has degree at most 1, that's not very interesting, right? A tree can have a vertex of degree 1000 as well. So I don't want to make it so strong. I want to find a sweet spot somewhere in the middle. Graph that has all vertex. No, not that one. That is too strong. Yeah.
In all of the like like the all of the vertex which have degrees less than equals to k minus 1, there must be one of them which connects to another vertex which has a degree of at most k.
It might be equivalent to what I have in mind, but it is too long for me to parse. So I will not attempt parsing it right now. Can you find something that is shorter? But it might be true. I'm not dismissing it. You can think about it later. I won't be able to process all of that right now. I'll give you a hint. Every subgraph of a tree is also a tree. No, not every subgraph. Sorry. Okay, I have to change that. Every subgraph of a tree is a forest because I may lose connected, right? And in fact, I can make this statement more. Every forest has a vertex of degree at most 1. Instead of showing the existence of a leaf, which is a vertex of degree 1, we could have done something weaker here. What we could have done is we could have used the fact that every forest has a vertex of degree at most 1. It could be degree 1 or it could be degree 0. For example, if I just have a bunch of vertices and no edges, that is a forest. There is no leaf because there is no vertex of degree 1. But there is a vertex of degree 0. Right? So I could have proved that every forest has a vertex of degree at most 1. And now I will use the fact that every subgraph of a forest is also a forest. And now the same proof works to show that every forest is two vertex colorable.
In our graph, it must happen that every subgraph has a degree. Every
Yes.
subgraph has a
Every
vertex.
subgraph has a vertex of?
At most k minus 1 degree.
Exactly. This is what we are going to do. Supposing I make it slightly stronger, in every subgraph, not only does this graph have a vertex of degree at most k minus 1, I'm going to strengthen this slightly. Every subgraph of this graph has a vertex of degree at most k minus 1. Supposing I give you a graph whose every subgraph, including itself, because a graph is a subgraph of itself, has a vertex of degree at most k minus 1. Then does it follow that the graph is k vertex colorable?
Yeah, now we can.
Yes, now we can induct, like the induction works.
Yeah.
Yeah, excellent. Good. So let's do that. So here is the general point. G is a graph whose every subgraph has a vertex of degree at most k minus 1. Then G is k vertex colorable. Does everybody agree with this statement? This is a
Yes.
generalization.
Yeah.
Good. This is the generalization of the fact that every forest is two vertex colorable. Right? In fact, if you put k equal to 2, you will get exactly the forests. The only graphs whose every subgraph has a vertex of degree at most 2 minus 1, which means at most 1. These are exactly the forests. I'll just make a point over here. If k is equal to 2, such graphs are precisely the forests. And by a forest, I mean any acyclic graph. Any graph without cycles. Yeah? Okay, good. All right, so now let's think. So now we want to prove the sixth color theorem. And to prove the sixth color theorem, we will use these ideas. We will use basically this observation.
So you'll have to show in every way, if you're given your graph which has come from a map, every subgraph of it should have a degree less than or equal to 5.
Good, good. But let me ask you now, if I just show that every planar graph has a vertex of degree at most 5, are we done?
Yeah, like
We just show that every planar graph has a vertex of degree at most 5. Then are we done?
Yes.
Yeah? Because every subgraph of a planar graph is planar.
Yes.
Right?
Yes. Yeah.
Exactly. So in fact, what we will do is now we will prove this. So it suffices, it turns out this is actually a true statement. It suffices to prove that every, I will put the word simple because if you don't put simple, then it is not a true statement. Right? You can always keep adding multiple edges and increasing the loop, increasing the degree, sorry. Every simple planar graph has a vertex of degree at most 5. If we prove this statement, we are done. We have proved the sixth color theorem. Yeah?
Yeah.
Okay, great. But before we prove this, let us think a step further, right? We also want to prove by the end of today's lecture, hopefully, that every planar graph is 5 vertex colorable. So, can I use a similar approach to prove the 5 color theorem?
You can, but is it true? You can, but is it true?
Is it true? Right. If it were true that we could change this 5 to 4, then we would have proved the 5 color theorem using the same idea. The problem is it is not true that I can replace 5 by 4. You can make planar graphs, infinitely many of them, where there is no vertex of degree at most 4. So every vertex has degree at least 5. And in particular, some vertex will have degree exactly equal to 5 because we will prove this statement. Right? So this idea cannot work for this does not work to prove the 5 color theorem. We will only prove the 6 color theorem using this. This is for 6 color theorem. Right? So for 5 color theorem, we will have to do something much more clever than all of this. Okay. All right. So the next goal is to prove this fact. Okay. Every planar graph has a vertex of degree at most 5. Everybody with me? Are there any questions or concerns?
No.
Okay.
It's clear till now.
Okay. So goal. To prove that every planar graph has a vertex of degree at most 5. Okay. So to prove this, we will use
If you show the number of edges,
Ah.
for each vertex, the number of edges, there's always E is not equal, E is less than or equal to 6 V. Then I think maybe because then what you're doing is you're trying to show that every vertex cannot have
Yeah.
6.
Yeah, so in fact, what we'll do is exactly what you are suggesting. We will first prove an upper bound on the number of edges. If we prove an upper bound on the number of edges in terms of the number of vertices, then intuitively it seems that we should be able to upper bound the maximum degree of a vertex. And in fact, that is what we will do. We will prove that m, number of edges, is less than or equal to 3n minus 6. This is actually the formula we will prove. M is number of edges. And n is number of vertices. Supposing we prove this, then do you all see why this statement is true? Supposing every vertex has degree at least 6, right? You all see, right? You all see the handshaking lemma, right? Everybody knows the handshaking lemma?
Yeah.
Okay.
Yes.
So if you know the handshaking lemma, then convince yourself that proving this implies this. Yeah. Okay. So now we will focus on this. Yeah. And in fact, yeah. So I will just put a line over here. I don't care about this vertex of degree at most 5 anymore. We will just focus on the bound on the number of edges. Handshaking lemma. I can explain the handshaking lemma. Okay. Let me ask you. Take this graph. Consider these vertices V, U, W, and X. And sum up the degrees of the vertices. Let me call this maybe U, W, X, and Y. So what I will do is I will sum up the degrees of the vertices. What do you get in this graph? If you sum up the degrees of the vertices, what do you get?
You get 10, right?
You get 3
10. 2
plus
plus
3,
3 plus
6
2.
plus 2 plus 2, 10. Yeah, thank you. You get 10. And you also observe that this is equal to 2 times the number of edges. In this example, there are 5 edges.
Yes.
Yeah. Okay, this is basically the handshaking lemma. You can prove it yourself. Sum of the degrees of the vertices is 2 times the number of edges. Now observe that if every vertex has degree at least 6, then you will have a contradiction to this.
But we do need to prove some base case, right?
Yeah, so in fact, this statement is actually false if n is too small.
Yeah.
I need n to be at least something.
12, right? 12 or something like
No need for that big. No, very small number.
Oh, there will be like 4 or something.
Try some examples. N,
One does
somebody
not
wrote
work.
2. Do you mean
One
greater
or
than 2 or do you mean greater than equal to 2?
Greater than 2.
greater than
Greater than 2 works, yes. So if n is at least 3, then we will prove this bound. Yeah, thank you. Okay.
I think we can use Euler's thing.
We will use Euler's formula. We will use Euler's formula. We will use the handshaking lemma, and we will also use the dual handshaking lemma. I need to tell you what the dual handshaking lemma is. Okay? Which is very similar to the handshaking lemma. So I'm glad that somebody asked what the handshaking lemma is. Okay, so actually let's also talk about the dual handshaking lemma. So this is a plane graph. So for a plane graph, instead of the degrees of the vertices, I can also sum up the degrees of the faces. I need to tell you what the degree of a face is. So I will take all the faces of my graph. This is only for plane graphs. And I will sum up the degrees of the faces. So can anybody tell me what is the degree of this face?
3.
3.
Like probably
What is
the
the
number
degree
of
of this face?
edges it is bounded
Exactly.
by.
This is also 3. And what is the outside?
4.
4. What do you get? 4 plus 3 plus 3. Again, you get 10, which is again 2 times the number of edges. This is called the dual handshaking lemma.
Oh yeah, because each edge is like counted twice, like by 2
Exactly.
regions on either side.
Yeah. So this is the dual handshaking lemma. This is the usual handshaking lemma. And we also have Euler's formula. These are going to be our ingredients to prove this upper bound. Euler's formula says that I like to remember without minus signs. Number of vertices plus number of faces is equal to number of edges plus 2.
So that means you want to show that if you substitute for m, the value of m,
Yeah.
should you show f is less than or equal to 2n minus 4? I think.
Okay.
Because over here, m is equal to n plus f minus 2. You can put that there, you can remove one of the n's, you get 2n minus 6 and f minus 2. So then you can remove it and you can say f is less than or equal to 2n minus 4. That's pretty much.
Okay, sure. I mean, I won't be able to follow this much arithmetic, so I will not try. I mean, I know how to finish the proof from here. So I will show you one way of finishing it, but there may be many ways of finishing it, right? So, I mean, yeah. One reason I do graph theory is because I don't like arithmetic manipulations. But anyways, the idea is to use this, to use this, to use this, do some whatever massaging you want to do, and prove that n is less than or equal to 3n minus 6, right? So, but I haven't proved Euler's formula, right? And I'm also not writing down rigorous proofs of handshaking or dual handshaking lemma. I'm just going to assume all of these things, and we will see one proof of this using all of these facts. Yeah. Okay. Okay. Any questions or concerns regarding the statements, the handshaking lemma, dual handshaking lemma, and Euler's formula? Everybody's okay with that?
The yellow box,
Okay.
which is less than equal to 3n minus 6, it's for planar graph, right?
This one? Yes, this is only for simple planar graphs with at least 3 vertices.
Okay, sir.
Yeah. Okay, good. All right. So now let's do it. I will erase this example. Okay. So what we will do is we will first sum up the degrees of the faces. Sum of the degrees of the faces of and I'm taking a planar embedding, right? So here I don't just have a planar graph. I will take a drawing in the plane. This is a planar embedding. Or if you don't like the word embedding, drawing. Because then I can use the dual handshaking lemma. I can talk about faces. Otherwise, I can't talk about faces. Sum of the degrees of the faces. I know this quantity is equal to 2 times the number of edges. Yeah. And somewhere you have to use this hypothesis, right? Without this hypothesis, number of vertices is at least 3, this proof should fail. For example, K2, 2 vertices joined by a single edge. This violates this inequality. There is only one edge, n is equal to 2. So you get 6 minus 6, 0. So what you get is 1 less than equal to 0. That's a contradiction. Right? So somewhere we have to use this fact. So the place where we are going to use this fact, if n is at least 3, then the degree of each face is going to be at least 3. So degree of each face is at least 3.
Right.
This is the fact I'm going to use. Okay, and this is because of this. Okay, so therefore, because all of these are at least 3, I will get
3f is less than or equal to 2m.
3f is less than equal to this. Yeah, thank you. Now I will use Euler's formula, and instead of f, I want to get rid of f. I will now use m plus 2 minus n. Yeah. Now can you all see from here that this is true?
Yes. Yeah.
Yeah.
Okay, fine. So there are some small things that I hand waved here. Let me just briefly address those things. So I want to just address these things quickly. So you see the example I gave you, I deliberately chose an example where the degree of every face, the boundary of every face was a cycle. For example, the boundary of this face, you said that the degree is 3, the degree of this face is 3, and the degree of the outer face is 4. You were able to tell me very quickly what the degree of each face is. Yeah. Now let me give you an example which is not so nice. K2. How many faces are there?
1.
There is only one face. What is its degree?
1.
Probably
But then
1.
this handshaking lemma fails, right?
Okay.
Yes.
I want the handshaking lemma to be true. So because I want it to be true, I will define degree in a certain way. Degree, you can walk around this face and come back to the original point. The number of edges in this walk is 2. So I start here and I come back here. The number of edges I have traveled is 2. This is how the degree of a face is actually defined.
So you don't need the 2m anymore, right? Exactly.
Sorry?
Since you're defining the degree in this way for this edge case, you don't exactly need 2m. It's already there since you're going through every edge coming back. So it's already.
No, so if you define degree in this way, turns out dual handshaking lemma is always true. Let's take one more complicated example. I just want to make sure that I'm telling you that there are nuances I'm kind of skipping deliberately. Let's quickly compute the degree of faces in this example. First, let's deal with the easy ones. What is the degree of this face?
3.
3. And the other one as well, 3.
What is the degree of the outer face now?
8.
8. That's right.
Yeah.
Okay. Yeah.
And now observe that 8 plus 3 plus 3 is 14. There are 7 edges in the graph. Right?
Yes.
One way to get around this kind of issue is to assume that you are dealing with 2 connected planar graphs. So in a 2 connected planar graph, you will never get such situations. In a 2 connected planar graph, every face boundary will be a cycle. And now it is easy to see why the degree is at least 3, because cycles of length 1 and 2 are not possible because our graph is simple. Okay, so there are multiple ways to deal with these issues. Either you define degree rigorously, or you just say my graph is 2 connected, because if you prove the statement for 2 connected graphs, then you have actually proved the statement for all graphs, and that needs an argument. So there are things I'm kind of glossing over, but those are things I don't gloss over in my actual course here, right? I mean, yeah. Okay. So, any questions, concerns? Okay, so is everybody happy with the fact that we proved m is less than or equal to 3n minus 6? This implies there is a vertex of degree at most 5. Now, by the previous discussion, because there is a vertex of degree at most 5, our graph is 6 vertex colorable. And every subgraph of a planar graph is planar. Right? This fact is also being used in the induction. Right? So I will take a vertex of degree at most 5. I will delete it. Now the smaller graph is again a planar graph. I will color it with 6 colors. Now I'll put this vertex back. Because it had degree at most 5, its at most 5 neighbors use at most 5 colors. I have a 6th color remaining in my palette. My palette has 6 colors. I will use a 6th color for this vertex. Okay, good.
But you can't use this for 5 then.
To prove the 5 color theorem?
Yeah, you can't use this for 5 then, right?
We can't. We will have to do something different. Yes. This is why the 6 color theorem is generally not even called a theorem, because it is, in the grand scheme of things, it is actually too easy. Whereas the 5 color theorem is not that easy in the grand scheme of things. How does 8 plus 3 plus 3 equal to 2 times 7 make sense? So the point is, let's go back to that example. The point is every edge is actually counted in the boundary of two faces. It's counted twice. So this edge, for example, it is counted twice in the degree of this face, and it is not counted any time in the degree of any other face. Whereas all other edges, they are contributing to the degree of two faces. They are contributing 1 to the degree of 2 different faces. Does that make sense?
We can also consider the dual of this graph.
Yeah, you can also consider the dual, but yeah, that's another way to do it. So the dual handshaking lemma is basically just the handshaking lemma applied to the dual graph. That's another way to do it, right? So if you want me to do that, I'll quickly do that as well for this example. But the thing is, it's dual. We have to define it. So here is the original graph. And now we are going to have 3 vertices in the dual. 1, 2, and 3. And I will draw the dual. For every white edge, I have a green edge joining the two faces. Now here is where the interesting part comes. This white edge, this is called a cut edge in graph theory. When you delete this edge, the number of components increases. This white graph has one component, one connected component. When you delete this white edge, you will get 2 connected components. One triangle and another triangle. These are called cut edges. For a cut edge, what happens is, on both sides, you will see the same face. So what you do in the dual, you draw this loop. Now you sum up the degrees of the green graph. 3 plus 3. And now what is this?
8.
8. Now you get 14, which is again 2 times 7. So that's another way to think of the dual handshaking lemma. It is just the handshaking lemma on the dual graph. It's just that in the previous lecture, I did not show you examples with cut edges because I did not want to deal with them. All right, but since you mentioned, I didn't have a choice. Okay, good. All right. Okay, questions, concerns? All good? All right, so we are done with proving 6 color theorem. Okay, so now we want to prove the 5 color theorem. All right. This is not that easy, but this is a lot of fun. So let's begin.
How did we prove the 6 color theorem? We proved the dual handshaking lemma, right?
Right. So I will quickly just recap. To prove the 6 color theorem, we basically proved this statement. Every simple planar graph is a vertex of degree at most 5. To prove this statement, we proved this statement. Number of edges is less than or equal to 3n minus 6. Whenever n is at least 3.
Okay.
Once we prove this follows immediately, and then the 6 color theorem follows immediately from this observation. Put k equal to 6, and you get that the graph is 6 vertex colorable. So that explains how we proved the 6 color theorem. And to prove this upper bound, we use the handshaking lemma, the dual handshaking lemma, and Euler's formula.
Oh.
Yeah. All right. Anybody else? Any other questions or concerns? Let's address all of them before we move on to the five-color theorem. Yeah. Okay. So, next goal. To prove the five-color theorem. Every simple planar graph and I don't even need simple, right? Because coloring does not depend on multiple edges and loops. So I just said every planar graph. Every planar graph is five vertex colorable. This is what we want to prove. Of course, to prove the statement, it suffices to prove for simple graphs because parallel edges, the multiple edges, they don't really affect the colorability. Right? Okay. And of course, we have to put loopless because if there is a loop, then you can't color the graph at all because the vertex should get a color that is not the same as its own color. That is a contradiction. Okay. So this is what we're going to prove. Every planar loopless graph is five vertex colorable. Okay. So let's write down a proof by induction and we will get stuck somewhere that we will discuss, right? And this will also give me an opportunity to write down the inductive proof that I never really wrote down until now. So, proof by induction on n number of vertices. Let's not worry about base case and all that. We will come to those discussions later. We'll directly go to the more interesting case. So, we know that there is a vertex of degree at most 5. Right? But this is not going to be enough as we discussed. So let's see. We know that there exists a vertex of degree at most 5. Yeah. So we will delete this vertex. Let V be any vertex. Let V be a vertex such that the degree of V is exactly equal, not less than equal to 5. Let us finish the nice case. What is the nice case?
Less than or equal to 4.
If the degree is less than equal to 4, then we are done by the same idea. Yeah? Okay. So, if the degree of this vertex for some reason happens to be at most 4, then I'll just make a drawing. This is my vertex. Let me just put 4 degree, right? Even the argument for 3, 2 works. So let's suppose these are my neighbors, V1, V2, V3, V4. Then I will simply delete this vertex. Now I have a planar graph. Every subgraph of a planar graph is planar. So by the induction hypothesis, this fellow G minus V is 5 vertex colorable. I will take a 5 vertex coloring of this fellow. Now I will put this vertex back into the picture. Its at most 4 neighbors will use at most 4 colors. Therefore, my palette has 1 color that is not used by the neighbors. That remaining color I will give to this fellow and I'll finish it. Yeah. Okay. If the degree of V is at most 4, then we are done. By the induction hypothesis. Right? The problem is, what if this fellow's degree is exactly equal to 5?
I think we'll have to look at the other, what's We can't exactly remove. We'll have to look at other stuff.
Give me a second. I'll just repeat since there is a request to repeat. So if the vertex has degree at most 4, I take the smaller graph G minus V. Right? Observe that G minus V is again a planar graph. Because every subgraph of a planar graph is planar. So by induction hypothesis, G minus V is 5 vertex colorable. Take any 5 vertex coloring of this graph. Observe that these 4 vertices will only use 4 colors because there are only 4 of them. The 5th color is free for this vertex. I will give this vertex the 5th color and I'm done. Is that okay, Ayush? Okay, thank you. Okay, are there any other questions or concerns? So the only problem is that vertex V has degree exactly 5. In this case, we are stuck. So the difficult case is when the vertex V has degree equal to 5. Yeah. This is really not that easy. So we are going to do some really cool things now. Are there any questions or concerns? I will go to a new page if that's okay. Or maybe I'll just make this smaller. Give me a second. I can make this smaller. Okay, good. So if there's a vertex with 5 neighbors and all of them have 5 distinct colors, then we have a problem. Yes, thank you. Exactly. So in fact, we can make a slightly stronger point here. We will do that. So in fact, let's make a small drawing. This is my vertex V, and these are the 5 neighbors. V1, V2, V3, V4, and V5. Again, I can try to use induction. That's a good point, right? So Rohan is saying that again we can try using, I'm trying to read your statement in another way. I can delete the vertex V. Again by induction, the remaining graph G minus V is 5 vertex colorable. The thing is we don't have any information about this coloring. If these 5 vertices V1, V2, V3, V4, V5, if they all use 5 different colors, then we cannot proceed. However, if they use only 4 of the colors amongst the 5 of them, then we may be able to, we are actually done.
So you have to do a recoloring.
No. So in the other case, we will have to do it. Yes.
Yes.
But first, let me just address the easier case. If V1 to V5, they do not have pairwise distinct colors, then we are done. Let me just convey this point. So in the same spirit as before, we can make a stronger point here. If V1, V2, V3, V4, V5 do not use pairwise distinct colors, so some color is repeated, then we are done. If they use only 4 colors, again the 5th color is free, and I will give the 5th color to vertex V. Yeah, everybody with me? So the difficult case is not only this degree of V is equal to 5, but all 5 V1, V2, V5, they all use distinct colors.
So unless they are connected, they can have different colors.
No. So that is a very important misconception, right? So if they have an edge between them,
right? But if
we
there is
know
a
they will
path,
get-
if there is a path, you can switch, alternate the colors.
No, let's not go too fast. Let me. So if there is an edge between them, if there's an edge between 2 vertices X and Y, definitely they will get different colors. If there is no edge between them, I have no idea whether they have the same color or different colors.
Yes, we cannot control anything.
Right? If there is no edge, I cannot actually say anything. Because by induction, I just know that the graph is 5 vertex colorable. I have no control on what this 5 coloring looks like. Right? So, yeah. So it could very well happen that there are no edges between any of these vertices, but still they all get different colors. Red, blue, green, yellow, pink. They use all 5 colors, but there are no edges between them.
So you'll have to change some things in the other thing maybe.
We will do that. We will do that. But you get this? You see this?
Yeah, right.
So,
yes.
Because it is very common in colorings to jump to the conclusion that, hey, because they are not adjacent, they have different colors. Right? So that is a conclusion we cannot make.
Yeah, no, I was just saying if that wasn't the case, because I was saying you cannot have an edge between all, since K5 is not planar.
That is true. So that is another way to. So we will not actually use K5 is not planar today.
Okay.
So, yeah. So that's so what you are saying is right. So this is actually a very interesting point. These 5 vertices, right? Ronit's point is that they can't all be adjacent with each other. Right? It is not possible that Vi and Vj are adjacent for every I comma j in 1 up to 5. Because if that happens, then you have a K5, and that is a problem because the graph is planar, it can't have K5 as a subgraph. That is actually one way to proceed in the proof. Today we will not use that fact. Today we will do a different proof. Yeah. Okay. And even that idea, it takes a while. So actually, it takes a while to complete that proof also. Right. So yeah. But anyways, there's another question. If we remove V1 and gave every edge different color and then removed edge remaining color, we are done or not? I'm not sure. We'll take that up later. Let me just continue on this track. So is this point okay? So I can conclude that the difficult cases degree is equal to 5 and V1, V2, V3, V4 and V5 receive all 5 colors. Does everybody agree? This is the hard case. Okay? This is the hard case. All right. So now we are going to do something interesting. And I want to point out here that in the proof of the 6 color theorem, we never took an embedding of the graph. We just used the fact that there is a vertex of degree at most 5. We deleted it. We use the fact that the resulting graph is again planar because it is a subgraph of the original planar graph. And we finished the proof by induction. We never took a planar embedding of the graph. In this proof, we are going to take a planar embedding, a planar drawing, and we are going to actually exploit the topology of the plane in a very, very nice way. Don't worry, you don't need an advanced course on topology. Okay, but there is a fact about the topology of the plane that we will use today. And that is the point I want to mention. The moment you are dealing with planarity, you are essentially dealing with the mathematical subject of topology. Because the plane is a surface and you need to use some fact about this surface. And so far, we have not used any facts about the plane in a very, very explicit manner. What was planar embedding? Planar embedding is just a drawing of the graph in the plane where the edges do not cross. Yeah. Okay, cool. All right. So, is that clear, Anirudh? Planar embedding? Okay, thank you. So now we will take a planar embedding. Okay. And for the sake of making this distinction clear, I will say G tilde is a planar embedding, popularly known as planar drawing of G. Yeah, everybody okay? And I'm going to draw this vertex and its 5 neighbors. And I want to point out some facts about planar embeddings. So now this is not just an abstract graph. This is a drawing in the plane where no 2 edges cross. This is my vertex V. This is my vertex V1. Observe that when you draw something in the plane, you can order if you draw a graph in the plane, like a planar embedding, right? There is an ordering of the vertices around every vertex. For every vertex, there is an ordering of its neighbors. It's a cyclic ordering. There is a cyclic ordering of the neighbors of the vertex based on how the edges have been drawn. Okay? So according to this cyclic order, I am going to label these vertices V1, V2, V3, V4, and V5. This cyclic ordering is important. Okay? And let me make some space here. Give me a second. I will move this to the center because I need some more space. Okay. Yeah? Everybody with me? So far, so good? Okay. This cyclic ordering is crucial. Okay. Okay. So we are here and we are in the difficult case. In all other cases, we are done. So in the 5 vertex coloring of G minus V, all these 5 fellows, they get 5 different colors. Okay. So why this keying or cyclic ordering is important? We will see that. So this cyclic ordering is important, will become crucial, right? So now let me give the 5 colors. Let's say color 1 is the green color. This is my color 1. Color 2 is the pink color. This is my color 2. Color 3 is the blue color. Maybe I should not use blue here. I'll use a different one. Sorry. With green, I will pair up maybe red or something. Okay, I'll put red as the 3rd color. This is my color 3. And with pink, I will pair up blue maybe. This is my color 4, blue. And finally, I will use maybe yellow for color 5. Okay, just in case anybody is having trouble with colors, this is green, this is pink, this is red, this is blue, and this is yellow. These are my 5 colors, and the vertices V1 to V5 get colors 1 to 5 respectively. Everybody with me? Are there any questions or concerns? Okay. This is where the fun is going to begin. All right. So, do you all agree that we have to massage this coloring? We cannot just take this coloring and give any color to this vertex V. There is no way to extend this coloring to a 5 vertex coloring of the original graph G. Right? So we have to make some changes to this coloring. Do you all agree with that point? We
Yes.
have to change the coloring. Okay.
Yes.
Great, thank you. So now we are going to discuss one of the silliest ideas of changing a coloring. Okay, it's a really silly idea, but that silly idea we are going to actually make it useful. Okay, so bear with me. If you give me a 5 vertex coloring of some graph, let's say the colors are green, pink, red, blue, and yellow. Can you give me a very, very naive way of getting another 5 vertex coloring? And this naive way should be completely useless from a
Just
mathematical.
permute the
Change the
colors.
colorings.
Change the color.
Permute the
Yeah,
color.
take 2 colors, take 2 color classes. So these are called color classes. Take 2 color classes, let's say the pink and the blue, and just swap them. Turn all the pink vertices blue and all the blue vertices pink. Do you all agree? This is a valid way to change and get another 5 vertex coloring. And do you all
Yes.
agree that it's completely useless?
Yes. I mean, the 5 different colors still remain 5 different colors.
Exactly, right? From a mathematical point of view, it's completely useless idea. Good. Sometimes useless ideas can lead to useful ideas. So now I want to look at it in a different way. So we are talking about two colors. So another way to think about what we just did is take the blue-pink subgraph. What do I mean by the blue-pink subgraph? By the blue-pink subgraph, I mean take all the blue and pink vertices and take all the edges that have both ends in the union of this vertex set. So both ends have to be, one end has to be blue and the other end has to be pink, because of course both ends cannot be blue because this is a 5 vertex coloring, right? So
This is two colorable.
yeah, this is a two colorable subgraph, right?
Now
So the
we
blue
can.
pink subgraph is a two colorable graph. In particular, the blue and the pink shows you that it is two colorable. So is everybody okay with blue pink subgraph? Right? So if I say yellow red subgraph, do you understand what I mean? Right? Okay. I will not write down the formal definition. Right?
Yes.
It is all the yellow and red vertices and all the edges whose ends are one yellow and one red. Okay. Good. So I want to repeat that naive observation. You can take the blue pink subgraph, for example, and just swap all the colors in that subgraph. Okay. That gives you another 5 vertex coloring. Good. Now I want you all to think about this and give me something more sophisticated. Take the blue-pink subgraph, or I don't know, blue-pink or whichever, green, red, whatever, doesn't really matter. Take the blue-pink subgraph and instead of swapping all the colors, can you do something more interesting?
Swap maybe only some of them.
But you have to be careful, right? If you just
Swap the colors of those who are connected to other
I like
colors.
that word, connected. Did you say connected?
Yeah.
Yeah, can you repeat your observation with the connected word?
Like swap the colors which are adjacent to other colors, like not the blue or the pink.
No. So, I want to take you back to your connected word. So take the blue pink subgraph, and I
Yeah.
don't want to swap all the colors. So this subgraph may be
So
connected or it may be disconnected.
only
Good.
the connected component which you are using in your fifth vertex is the
Okay.
last vertex.
Right. So, okay, let's repeat this. So you look at the blue pink subgraph. If it is a connected graph, I will just swap the colors. I can't do anything fancy. But what I'm interested in is what if it is a disconnected graph? If
Then you
the
can swap
graph
and
is
it'll work.
disconnected, then I can take one component and I can swap the colors in that component. Do you all agree? Okay, let me make a drawing. Let me make a quick drawing. I'll go to new page. Supposing my blue pink subgraph has two components. Supposing this is my blue pink subgraph. Supposing this is my blue pink subgraph. And let us suppose it has two components, H1 and H2. Supposing it could have three components, I don't know. Then what I can do is I can take this component and I can swap in this component, but not swap here. Okay, no swap. Then if I do this, I have another 5 vertex coloring. Everybody agrees?
Yeah.
Okay. So if the blue pink subgraph, or for any two colors, if the subgraph is disconnected, I can actually do something more intelligent. I can take one component and just swap the colors in that component. Then I have another 5 vertex coloring of my graph.
Yes.
Here it is very important that we are taking the whole component. If I just take part of the component, it doesn't work.
Yes.
In general, I have to take the whole component, then it works.
Yes,
This is
but still, like the vertex we want to color, like if it's connected to, like if you're changing the colors of the component, both the blue and the pink will be in the same component. It still doesn't
Yeah. So
directly finish.
yeah, we will get back to the proof. But is this part clear? Just this part, right? This is a lemma in isolation by itself. Yeah. Okay. So we will use this idea in a very, very crucial way. Okay. But let's go back to the previous point. We know that we have to change the colors here. Okay. We know that we have to do some changes here to make progress in this proof. Yeah. Everybody with me? Can I repeat which part?
Sir, subgroup part.
Yeah, so the observation is just we can swap the colors in any one component of the blue-pink subgraph, and we will get a different 5-vertex coloring. That is the observation. And I will repeat this observation in the context of the proof again. Yeah. So let's go back to the proof. So here we have, let's repeat, let's see what we have, right? So I sent this as a private message to you. I don't know how to check private messages. Okay, I don't know. Yeah.
So this is what you just read is, but I was saying that I think I see it, so I just wanted to tell you.
Okay, cool. Okay, cool. Thanks. Yeah. Okay, so let's go back to the proof. We took a planar embedding of our graph, and we have these vertices V1 to V5 in the cyclic ordering around the vertex V according to this planar embedding. Okay. Now what we will do is we will take we will consider the G13. So by G13, I mean the green-red subgraph. Is that okay?
Yes.
I will take the green-red subgraph. So just right, this is the green-red subgraph. I will first look at this subgraph. Okay. So there are two possibilities. Either these two vertices are in the same component of this graph, or they are in different components. In which case are we done?
If they're different, then we
Different
are done.
components, then we are done.
Excellent. If
They're
V1
different.
and V3 are in different components of G13, we are done. Everybody
Yes.
agree?
Yes.
Okay, excellent. Let me write that down. If V1 and V3 lie in distinct components of the graph G13, then we are done. And I will repeat why we are done, but I don't have space to write why we are done. So if this is the case, I will look at the G13. They are in different components. So that means there is a component that contains V1. There is a component that contains V3. These are two different components. So what they are saying is just swap the colors in this component. Make all the green vertices here red and all the red vertices green. Now this vertex is red. This is also red. So I have the green color free for this vertex. I'm done. Proof is finished. Right? So swap, which means this becomes red. This will become red. This will remain red because I did not swap here. No swapping here. And now I will give the green color to this fellow. And I have a 5-vertex coloring of my graph because this is actually now the red color. Everybody with me?
Yes, sir.
Okay, excellent. So now we will assume that they do not lie in distinct components. They lie in the same component. In this case, we still have to make progress. Okay. So let's write down.
If
Now-
they're in the same component, what if we try to take different colors? Like we are taking 1, 3. What if they are in the same component, we try
That's
to
exactly
pick
what
one
we will
another?
do. That is exactly what we will do, and we will use a fact from topology to finish the proof. Now suppose that V1 and V3, they lie in the same component. Lie in same component. But before we go to another pair, we will do something else here. Same component of G13. Okay, does everybody agree? This is the difficult case. Now this is the difficult case. We will keep
Yes.
changing the goalpost. Yeah. Now this is the difficult case. Okay. Good. Let me make some changes here. I want to erase some things. But by the way, before I erase, are there any questions about this idea? Is everybody convinced by this point? Or are there any questions regarding this distinct component case? Okay, everybody's convinced? Thank you. All right, so now let me erase a few things. Let me erase this green color. Okay, good. So we are back to the original situation. Green, pink, red, blue, yellow. Now we are in the case where V1 and V3 lie in the same component. What does it mean for two vertices to be in the same component?
There's a path connecting
There is a
them.
path. There is
Yeah,
a path
it's
between
usually
them.
those two colors.
Excellent. There is a path between V1 and V3 in the graph G13. There is a path between V1 and V3 in the graph G13. What does this path look like, by the way, just out of curiosity? What do the colors look like on this?
Alternating colors.
They are alternating colors. They are alternating. Let's do that. Alternating colors. So there's a green vertex. I have to put red here, green here, green here, green here, maybe green here. And now let me put the red vertices. It shall be alternating. So this will be red. This
So
will
an
be
even number of vertices between, right?
true, true. Yeah, because it is alternating, you can also talk about the parity. Yeah. Does everybody agree? This is what the path looks like. There is a path. There exists a path joining V1 and V3 in the graph G13. Let me call this path P13 for the lack of creativity. So this path is P13. Yeah? Okay. Good. Are there any questions or concerns? This is the path in G13. Let me just write down. So this implies that there exists a V1, V3 path P13 in the graph G13. Okay. Christmas colors. Okay, good. So now what do we do? So this did not work, right? We tried to play the swapping game and we got stuck. So now we want to play the swapping game on another pair of colors. Yeah?
So are we arguing that when we also look at the paths P24, they intersect in some way because
2 and 4. This is a good one. I like this 2 and 4. So what we will now do, observe that this is a cycle. Observe that there is a cycle here. This path along with these two edges, V2, V1 and V2, V3. This is a cycle. Inside this cycle, there is a vertex V2 and outside this cycle, there is a vertex V4. What we will do is we will pick this inside one V2 and the outside one V4. We could also pick V5, but of course it is more natural to choose 4 than 5. So I will choose V2 and V4 and we will look at the graph G24, the pink blue graph. Yeah, we will look at G24 and we will ask the question, where are V2 and V4? Are they in the same component of G24 or are they in different components of G24? That's where the inside outside comes in. That's right. This is where the cyclic ordering will be used. Thank you. Right? So the question is, are V2 and V4 in the same component of G24? Or can we conclude somehow
They have to
that
be in
they are actually in
different.
different components? Yes, can you repeat? Yeah.
They have to be in different
They
components.
have to be in different components. This
Because
is
Because it's
like
a planar graph.
yeah, it's a planar graph,
right.
so it
We
cannot
will use
intersect.
topology here. What you are saying is correct. And this is where we are going to use a theorem in topology. But I will give you the exact theorem of the statement later, or maybe I will not even give it to you. But we will just use it anyways, right? So let's just see. So the question is, maybe I'll erase some things here. Erase this. Let me just write down this question so that everybody is on the same page. The question: can V2 and V4 lie in the same component of the blue-pink subgraph G24. This is the burning question. Can these two vertices V2 and V4 lie in the same component of G24? Suppose the answer is no. Then I want to convince you that the proof is finished. Supposing we answer that the answer is no, then I want you all to think about it and convince yourself that the proof is finished.
It's basically the previous case.
Exactly. Previous case. Yeah?
Yes.
Okay. So if we prove that the answer is no, we are done. Okay. So why should the answer be no?
Suppose it is yes, so they're in the same component. Then there is like a cycle in G2. There's a path in G24, except because they are on the 2 and 4, V2 and V4 are on the opposite sides of this G13 path. It has to intersect somewhere, and because it's planar, the intersection point also has to be vertex, which cannot be true.
Like this, right? Supposing they are in the same component, then you take a path P24 going from V2 to V4. Then observe that this path, it starts at V2, which is inside this cycle. It ends at V4, which is outside this cycle. So it will have to leave the cycle. In order to leave the cycle, it will have to go through some edge, because the vertices are actually pink and blue, whereas the vertices on this cycle are green and red. So it has to hit the cycle somewhere on an edge. And now this point is a contradiction to planar embedding.
Yes.
Yeah. Okay. So we use the fact that if you have a cycle in topology is what they call a simple closed curve. So what we are actually using here is a fact in topology. Okay. So what we are actually using is called the Jordan curve theorem. I want to briefly tell you what the Jordan curve theorem is, and you will almost laugh at me for calling it a theorem. And that is actually good. Right? Okay. So is everybody with me? Is the proof clear? So I will tell you briefly what the Jordan curve theorem is. Without actually writing it down. Let's not go to 3 dimensions and all right now. Let me just focus on Jordan curve theorem for plane. I think there are some results in higher dimensions and surfaces, but I don't know much about it, so I'll just skip it for now. But anyways, the Jordan curve theorem says if you draw any simple closed curve in the plane, then it breaks the plane into two parts. The interior, this is my curve, simple closed curve. You break the plane into two parts, the interior of the curve and the exterior of the curve. And if you take a point in the interior, if you take some point, let's say I use a red color. If you take some point in the interior and you take another point in the exterior, and if you want to go from the interior point to the exterior point, somewhere you will have to cross the curve itself. This was taught in 3rd grade. Good, I like that. So let me tell you my own history with Jordan curve theorem. I'm not going to define things. I'm just going to leave it a bit vague right now. So I was in a graph theory course during my master's at Georgia Tech. And I was taking graph theory course with Robin Thomas, who is one of the people who improved the proof of the 4-color theorem in 1997. So I learned graph theory from Robin Thomas first, and he told us the Jordan curve theorem. And there were two kinds of people in the classroom. People who came from math backgrounds and people who did not come from math backgrounds, mostly people from computer science backgrounds, like myself. And the math background people were fine, yeah, whatever, Jordan curve theorem, maybe you've seen it, been there, done that. But the CS people were a bit confused. Why the hell is this a theorem? Isn't it like obvious? So I raised my hand and I asked Robin, why is this a theorem? This seems obvious. And the math folks burst out into laughter. And the CS folks kind of looked at me thankfully because they all had the same question. And Robin did not laugh. Robin just smiled. And he went on to explain that this is a statement about all simple closed curves. All simple closed curves in the plane. Most of the times when you think of a simple closed curve, you think of a circle, a convex polygon, etc. Those are actually easy to visualize, and it is easy to see why this theorem actually holds for them. However, in general, simple closed curves need not be that simple. Like the one I have drawn here, it's not that simple. And because it is a statement about all simple closed curves in the plane, it's not very clear why this should be true. Why can't you draw a very, very complex simple closed curve and get a contradiction somehow, right? I mean, so valiant sacrifice. Thank you. So anyway, so that's the point I want to make, that the Jordan curve theorem looks like a very innocent statement that should not require a proof. However, it does require a proof because it actually deals with all simple closed curves in the plane. And if you are more interested in reading about it, Robin told me to check out space filling curves. So there is this thing called space filling curves. Don't ask me to define them. You can read about it. So these are like really, really strange simple closed curves that fill up the whole space in some sense. And yeah, so now it looks difficult to prove, right? And yeah, 3 blue, 1 brown probably has a video about this, much better than I have. So yeah, please check out 3 blue, 1 brown. Anyway, so this is yeah, so can't we just sort of tweak a circle part by part? Maybe. I won't get into the Jordan curve theorem. I don't even remember the proof. So Robin actually proved it for us. I typically don't prove it in my lectures. I just state the Jordan curve theorem as a fact from topology, and then I use it in graph theory, mainly for planarity. So this is not a thing where I'm an expert, right? But we are basically using the Jordan curve theorem when we say that there is a crossing here, and let me not use the red color. There is a crossing over here. That is where we are using the Jordan curve theorem to finish the proof of the 5-color theorem. Yep. Okay, so we have therefore proved the 5-color theorem. Let me quickly do a recap of the proof, just for everybody's sake, right? So we are trying to prove the 5-color theorem by induction on the number of vertices. So we use the fact that there is a vertex of degree at most 5. We deleted that vertex and we got a smaller graph G minus V, which is a planar graph. So by the induction hypothesis, G minus V is 5-vertex colorable. And we quickly observed that the only difficult case is when V has degree exactly equal to 5 and all 5 neighbors use all the 5 colors. In other cases, we are done. So we came to the difficult case. Degree is 5 and all 5 vertices receive all 5 colors. So we took, now at this point, we took a planar embedding of the graph. And we labeled the neighbors of the vertex V in the cyclic order as per the planar embedding from V1 to V5. And we considered the colors to be 1 up to 5 respectively. So V1 gets color 1, V2 gets color 2, and so on. Now we use the cyclic ordering, and we use the idea that if you take any subgraph, by two colors like red-green subgraph, you can take a component of the red-green subgraph and swap the colors in that component, and you have another 5-vertex coloring. So we use that idea. We took the red-green subgraph and we observed that if 1 and 3 belong to different components of G13, then the proof is finished. So the difficult case is when V13 belong to the same component of G13. Now, because they belong to the same component, it follows that there is a path P13 joining V1 and V3 in the graph G13. So we took that path. That is an alternating path. By the way, these are called Kempe chains in graph theory. These paths that alternate between two colors, they are generally called Kempe chains. And they are very useful in chromatic graph theory. So this idea of alternating colored paths was actually used by Kempe. And then he would use that idea to prove the 5-color theorem. Right? So we got a Kempe chain between V1 and V3 in the graph G13. We call this the path P13. Now what we did is we could not play the swapping game on 1 and 3. So we are now going to try playing the swapping game on 2 and 4. And the key point is 2 is inside this cycle or inside the simple closed curve, whereas 4 is outside the simple closed curve. This is the fact we are now using. Because of the Jordan curve theorem, there cannot be a path between V2 and V4 in the graph G24. Because there cannot be such a path, it follows that V2 and V4 lie in distinct components of the graph G24, the blue-pink subgraph. And now we are back in this case. We will just swap the colors in one component, and now either the blue or the pink color will not be used, and we will give that color to the vertex V, and proof is done. QED. On what lines does the proof of the 4-color theorem go? I am not qualified to answer that question. So I have never really sat down and read the proof of the 4-color theorem. They use Kempe chains to the best of my knowledge. They use these ideas, but they use a lot more. There are things called the discharging method, which I am not really an expert on at all. I have seen it at some point in my graduate studies, but in my own area of research, we don't use these techniques. So yeah, I'm not really into this. But yeah, you can check out, I'm sure there are good resources for the 4-color theorem. I don't even know what good resources to point you to. I typically refer Bondi and Murthy for my course. And Bondi and Murthy, they do give some idea about how the 4-color theorem is proved. And I have never really gone through all of it. So I just, I won't get into it. Yeah. But yeah, definitely they use Kempe chains and they use a lot of other techniques from chromatic graph theory. Yeah. And another thing I suggest you all try later on, try to see why only these ideas are not sufficient to prove the 4-color theorem. I have tried at some point when I was a PhD student, but it is probably best to try it yourself, right? So see if you can try to use the same ideas to push from 5 to 4 and see when you get stuck. That will probably give you a deeper appreciation of this proof, right? Why we can push it to 5, but why we are not able to push it to 4. Yeah. All right. Any other questions, concerns? Okay, it doesn't have to be about this proof, but if there's anything else, I'm happy to discuss. We have another 10-15 minutes, or we can conclude earlier. Is this all in the course you teach? Yes, yes. So in fact, if you want to see, if you want to go, if you want to see all the details written down and everything, I strongly suggest checking out my YouTube channel. So all of these things are in the course. But of course, in the course, I will use a lot more graph theory formalism that I tried to avoid here. For example, when I told you the dual handshaking lemma, I kind of skipped some details, which I then address using some example. So yeah, in the course, I have a lot more details. You just search Nishad Kothari IIT Madras, you should find my YouTube channel right away. If you don't find it, just send a message to Sai or somebody. Yeah. And I'm also happy to share. You can get my number from Sai or someone. I don't want my number to be on the YouTube channel. Right. So, but yeah, some of you have my number, so you can probably share it with the other people who are in this group, but don't share it with random people, please. Yeah. Yeah. And that's my YouTube channel. Thank you. And even if you are not a student at IIT Madras, which I'm sure you all are not, you can audit my course anytime. So even students from IIT Bombay, CMI, etc., have audited my course through my YouTube channel. And I typically send them the assignments privately, and they can submit the assignments, and I give them marks and feedback. Of course, the feedback is more important. The marks is not so important. So yeah, you are welcome to audit my graph theory course whenever you like through my YouTube channel. The assignments are not available on the internet. I hope so. But the lectures are available on the internet. Good. Oh yeah, I am a faculty member, and part of what we do apart from teaching and other activities is research. So yeah, I have. I don't work on open problems by myself these days. I mostly get PhD students to solve open problems, and I guide them in the process. And that is something I really enjoy. So of course, I have some contribution, but they are the ones who are supposed to solve the problem.
Sir, is the problem simple enough that you could explain it to us what the problem is, or we can try?
No, so you can check out. So basically, what I would suggest is check out my YouTube channel. There is a playlist there called Talks by Students, and there you can actually watch one of the talks. I would say it may be difficult to follow those talks if you don't have complete knowledge of my structural graph theory course. You may be able to follow at some level, but basically you would need modules 2 and 5 from my graph theory course. Module 2 is connectivity, and module 5 is matchings. So if you have done my modules 2 and 5, then you would be able to follow those YouTube talks. Recently, two of my students, Aditya and Narayana, they graduated, and their talks are on my YouTube channel. And then there is a PhD student who actually did their master's defense yesterday, Santosh. And Santosh's talk is also now on my YouTube channel. Unfortunately, the recording was not very good because of some technical error. But for the other talks, the recording is actually quite good. I can give you a short glimpse of one of the problems that one of my students is working on. But I won't go into exact problem statement and all. I will just leave it a bit vague. Right? So maybe I will talk about the problem that one of my students solved, who's already graduated. So let's go to this graph. This is one of my favorite graphs. You'll keep seeing, I keep drawing it. So this is a 3 regular graph. Right? This is a 3 regular graph. And not only is it 3 regular, it is also 3 connected. If you delete any vertex, any 2 vertices, the graph is still connected. The remaining graph is still connected. Okay? So let's do it's actually connected. A lot of things are connected to the 4-color theorem in a strange way. So we know that, right? So Tate said that if you can prove that all such graphs that are planar are 3-edge colorable, then you have proved the 4-color theorem. So for 3 connected 3 regular graphs, if you prove that planarity implies 3-edge colorability, then this is basically the 4-color conjecture. You all agree? Yeah. And remember, 3-edge colorability is the same as 3 disjoint perfect matchings.
Yes. Yeah.
Yeah, this is something we discussed last time. I'll quickly show you the 3 disjoint perfect matchings. This is one. This is another. And then the remaining edges is the third perfect matching. Perfect matching means, think of your edges being colored, let's say the blue color. If you look at any vertex, you should see exactly one blue colored edge. That is called a perfect matching. If at every vertex you see one blue colored edge, then the blue colored edges, they form a perfect matching. Yeah. I will come to the text questions in a bit. Yeah. So this is what a perfect matching is. So this is what Tate proved, that you just need to show that all planar 3 connected 3 regular graphs have 3 disjoint perfect matchings. And this statement is actually false if you remove planarity. You need planarity. The smallest counterexample is the famous Peterson graph. So in the Peterson graph, which is this graph, in this graph you can prove that this is not 3-edge colorable. Which means it does not have 3 disjoint perfect matchings. However, it does have a perfect matching. Perfect matching is quite easy to see. Just take these 5 edges, for example. This is a perfect matching. So what is true? Peterson also proved in 1891 you don't even need 3 connected, you just need 2 connected. Every 2 connected 3 regular graph has a perfect matching. Okay, so this is something Peterson proved back then. In fact, something stronger is true. Not only is there a perfect matching, for every edge you can find a perfect matching containing that edge. Okay, so this was proved by Schoenberger. Schoenberger proved in 1934.
Does it tell you how many perfect matchings there are going to be in total?
Sorry, can you repeat?
Can you tell me how many perfect matchings will be in there in the whole graph if you put them all together?
This is very interesting. So this is so I'm coming to this point. So let me just point this out. Schoenberger proved a stronger statement. This is 1934. In a 2 connected 3 regular graph. In a 2 connected 3 regular graph. For every edge, there exists a perfect matching containing that edge. Each edge belongs to some perfect matching. Okay, is this statement clear? And you can see this here. Of course, this is a simple example. This is planar, so this should actually be 3-edge colorable. So that means there are 3 disjoint perfect matchings. That means every edge will belong to some perfect matching. This is only for planar graphs. But even for non-planar graphs, the statement is for any edge, there is a perfect matching that contains that edge. Okay, so this is not about planarity. This is for all 2 connected 3 regular graphs. So now you can ask more questions. Can you count the number of perfect matchings? Turns out this is one of the most difficult problems out there. We don't know how to count number of perfect matchings. In fact, even proving lower bounds on the number of perfect matchings is very difficult. So one of the big open problems in this area was to show that there are exponentially many perfect matchings. As n grows, there is some n to the power something perfect matchings in every such graph. And this was actually a major open problem that was solved in 2010. But I'm not going to go there. I'm going to take a slightly different turn. I'm going to ask, for any given edge, how many perfect matchings contain that edge? Okay.
Yes.
For a given edge, how many perfect matchings? Yes, this was solved. So it has been proved that there are exponentially many perfect matchings in two connected three regular graphs. But the question I'm going to ask now is, for a given edge, how many perfect matchings contain that edge? And I'm going to ask a very specific case. What are the edges that belong to only one perfect matching? Is it possible? We know that every edge belongs to some perfect matching. Is it possible that there are edges that belong to exactly one perfect matching? Okay, so are there edges, or could there be edges rather? Could there be edges that belong to exactly one perfect matching? And here is a small exercise for all of you. For this graph, the triangular prism, can you tell me, are there edges that belong to only one perfect matching? And how many edges are there if there are such edges?
All edges.
No, think again. In this graph, let me label the vertices 0, 1, 2, 3, 4, 5.
Six of them.
Sorry?
Wait, no.
Yeah, did you say 6?
I thought six, but no.
Yeah, you're right,
Seems
6.
like all of
It is 6.
6.
There are 6 edges that belong to exactly one perfect matching.
So there's more perfect match. This is not the only perfect matching which can happen.
I have shown you 3 perfect matchings. There is a 4th perfect matching. Right? I have shown you red, blue, and green.
Yes.
There is one more perfect matching in this graph. 0, 1, 1, 2, 3, 4, 4, 5. 0, 1, 1, 2, 3, 4, 4, 5. There are 2 more. You are missing 2 more.
0.
So somebody has mentioned 0, 3, 1, 4, 2, 5. That is the 4th perfect matching. So there is a 4th perfect matching. Somebody has given the 4th perfect matching. It is these 3 edges. This is the 4th perfect matching. It turns out this graph has exactly 4 perfect matching. That is not too difficult. I will give it as an exercise. So now 0, 2 and 3, 5. Yes. So do you see that the triangle edges, the edges that are in the triangle, those are in exactly one perfect matching. However, the edges that are not in the triangle, they are all in exactly 2 perfect matchings. Yeah. So these edges are called solitary edges. Yes. Yes, there can be such edges. And we call these edges solitary edges. So one of the things Narayana proved, in a 3 connected 3 regular graph, no matter how many vertices you have, there are at most 6 solitary edges. You can't have more than 6. At most 6 solitary edges. This is not true if you drop 3 connected and you make it 2 connected. In a 2 connected 3 regular graph, you can actually have many more solitary edges. I believe the correct number there is n divided by 2, where n is the number of vertices, but there are small counterexamples up to 8 vertices. Yeah, so up to 8 vertices you can find counterexamples. But once you make the graph 3 connected, 3 regular, you can have at most 6 solitary edges. Okay. And to prove this, we use a lot of matching theory. There's a lot of matching theory that goes into it. The proofs are actually not that difficult, but the amount of theory one needs in order to go through all of this, it takes time, right? So first you would, if you're interested, you would first have to complete the structural graph theory course or some equivalent course. In particular, you need the modules 2 and 5, connectivity and matchings. And once you're done with those modules, then you will need some more matching theory, which is not covered in the course, but that is mostly covered in the papers itself. So the paper we put on archive, which we have submitted to a journal, it typically contains, we try our best to write self-contained papers, but of course it is not possible to write completely self-contained papers, right? So typically you may have to go through some textbook and some basics. So there is in the last year, there was a book published called Perfect Matchings. So this was published in 2024 by Lucchesi and Murthy, USR Murthy being my PhD advisor, who passed away earlier this year, unfortunately. So Lucchesi and Murthy, they published a book in 2024. In fact, in the coming semester at IIT Madras, I'm giving a full course called Matching Theory based on this book. And I will be surprised if there is any place in the world where you can find a full course on matching theory based on the book published in 2024.
So what are those two names again? I didn't quite get.
Sorry, Lucchesi and Murthy. Let me write it bigger. Lucchesi and yeah, this is the same Murthy from Bondi and Murthy, which is a famous book for graph theory that I follow. Right, so if you're interested in graph theory textbook, I would recommend this book. And this is for matching theory. This is 2008. And this is 2024. Yeah. Bondi is John Adrian Bondi. He's a French mathematician. And Murthy is USR Murthy. Yeah. Okay. So now there are some questions in the text that I have not addressed. But before that, I can address other questions related to this, and then I can go to the text questions. Okay. So, yeah, I'll start a bit early. Let's see. YouTube channel. Okay. You mean the course playlist in YouTube only? Yes, I mean the course playlist in the YouTube channel. Yeah. So in my YouTube channel, there are two courses called Structural Graph Theory. There is a first offering and a second offering. I would recommend the second offering. The second offering is better than the first offering, as you would expect it. Right. For math interested people, would you recommend IITs in a math or something like CMI? So I think it's better if we stop recording at this point. After that, I'm happy to address more questions. Yeah.
Okay. Okay,
Yeah.
wait, let me see how I can do that.